So apologies for the technical glitches. So please go ahead.
Okay, so can you hear me remotely or locally? Okay, so I'll get started. So hi, my name is Zhuyang from University of Minnesota. So today I'm going to talk about our paper, Logarithm and Program Testing. So this is joint work with Favonia, who is my advisor. So this title, well, looks a little weird, especially the word logarithm. It's quite confusing. But unfortunately, I can only explain it at the very end of this talk. So if you are really curious about what logarithm is, please bear with me. So I will start with program testing. For program testing, actually I'm talking about testing parametric polymorphic functions. So, so for polymorphic functions, we are trying to test them effectively and efficiently. In particular, we want to reduce the number of test cases we need to test a polymorphic function. But before looking into a polymorphic function, let's first try to test a simple monomorphic function, the plus function here, which takes a pairs of integers and returns an integer. And here are three very simple test cases here. Well, as trivial as they look like, they are actually equally important. They are all necessary for completely test this function. Why? Because if there is some evil programmers like me, I might want to write 1 plus 1 to be 42 or something to really terrify or confuse my users. And I guess I will be fired later. Well, anyway, so it means that we actually need to try all possible pairs of integers to completely test this monomorphic function. So all test cases are necessary here. So that's the testing for a monomorphic function. So how about a polymorphic function? So this is the function from a pair of A's to an A. And we want it to be the first projection function. So it should return the first component of the input. And here are some test cases I listed here. Because it's polymorphic, we can actually instantiate it with different types, like integer, Boolean, or unit, or maybe list or trees. And then we can give it different pairs of elements to test this function. Well, however, not all test cases here are useful. So some of them are redundant or even useless. Well, so for example, for the integer type, the last one, the 0, 0 test case is absolutely useless because it will always return 0. So we cannot tell whether it's the first 0 or the second 0. So even the function is wrong, even it's the second projection, we cannot tell. So that's a useless test case. But on the other hand, the first two, the 9, 0 and 2, 5, these two are good. They're pretty good because we know it must be returning the first one, not the second one. So for the unit type, this unit type is actually really terrible because there is only one element in this type. So the only input we can provide is 2 units. And it's actually the same as 0, 0, because it will always return unit. For the Boolean type, well, as you might guess, the true test case is also useless because it will always return true. But false true is pretty good. So in the end, we have 3 test cases. These 3 test cases that are pretty useful for testing this function. And actually, any one of them is sufficient for testing this. So from these three, we can discover a pattern. So as long as the two elements in the input are different, then this test case will be sufficient for testing. So what we really need are two different elements in the input. So the Boolean type will be a perfect candidate because the Boolean type exactly have two different elements, false and true. So it can be proved that the Boolean type is actually the minimum type or smallest type that we can find to test this function with only one input, only one test case. All right, so the next example is the generalized n-array projection function, and we still want it to be the first projection. So it's from an n-array tuple to an A. And if we think about the possible ways to implement it, so it's taking an tuple from E1 to En, and it must return one of them, right? So following the same idea as we see in the previous example, actually we only need to make all these elements, the E1 to En, different. So as long as they are different, we can distinguish them in the output. So we can actually put 1, 2, 3 to N as the input, and using a type integer, or any type with at least n elements. So, so I'm using integer here because it's easier for presentation, but any type with n elements will work. For example, like a user-defined data type. So the final example is the reverse function from list of A to list of A. This looks much more difficult, but actually, if we think of a list as a tuple, but of arbitrary length, then we can actually do the same thing as we did for the tuple. So basically, for every length, we will give it an input. Like the test cases here, so for every length, we build a list from 1 to the length. So for this example, we need integer or natural or any type that's isomorphic or larger to natural number, and these test case and these lists as the inputs. All right, so from these three examples, the first projection for binary product, n-array product, and reverse function, actually we can see testing polymorphic functions is very different from testing a monomorphic function, because we don't have to try all the types and all the inputs. We only have to try, for example, here we only need one type and only a few inputs to test this function completely. So that's what our work mainly about. So we are considering a more general class of polymorphic functions from alpha A to Fa. The F here should be a functor. And we proved that we can find a special type and some special inputs. So these are sufficient for testing the function F completely. So we proved it on paper and implemented a tool in Haskell. That tool can work with quick track or small track to property-based testing libraries. And it's written in template Haskell to deal with the type expressions. And our theory works on the Phoenix fragment of system F with product types, sum types, function types, and inductive types. But we do require the inductive types to be strictly positive. So we can handle data structures like list or binary trees or something like that. So the theorem we proved in the paper looks like this informally. So the theorem is basically saying that suppose we have a reference implementation f, so f is correct, and our actual implementation is f prime. So that's the function we want to test, the f prime. And so the testing we are doing is to compare these two functions. And so we have a mechanical way to construct a special type, A star, the A star here, and a collection of inputs, B star, such that if we want to check these two functions are equal, it's sufficient to test for any special inputs, the output of these two functions are the same. So as I said before, the A star and E star can be calculated mechanically, and they are calculated directly from the type alpha A. And the way to calculate the special type A star is called the logarithm. So the special type we need is exactly the logarithm of alpha A, the domain type. Now it's time to explain the logarithm. So if you still remember the n-ray projection example, so it's taking an n-ray tuple to an A, and we have already discussed that it's sufficient to test only one input, which is the tuple 1 to n. So, and the idea is we need to find n different elements to put in the input so that we can distinguish them in the output. So what we need is a type with n different elements. And if we take the logarithm of the domain type, which is NA multiplied together, it's actually, it will give us n. So we take the logarithm with base A of A to the n. The answer is n. So the logarithm will give us the number of A in the input intuitively. So it makes sense is because we do need n different elements, and the log with base A is exactly the number, exactly that number we want. Okay, so also there are some previous works on testing polymorphic functions more effectively and efficiently. The first one is a paper testing polymorphic properties in 2010. And their theory works on a specific class of functions, well, in this particular form. Well, and actually their theory can handle more general polymorphic functions, but it requires an ad hoc and complex process to transform the general polymorphic functions into this particular form. But our work can calculate it mechanically. The second one is a Haskell library called Metamorph in 2017. So that Haskell library is very similar to our library, and it's inspired by the first paper. So in that Haskell library, its implementation actually looks quite similar to our logarithm operations and other operations. But Metamorph can only handle one type variables, and it cannot deal with general inductive types. So to conclude my talk, we proved that we can actually mechanically construct a special type and limited number of inputs to completely test a polymorphic function. And in the future, there are a few things we can work on. For example, currently, our logarithm operation will not always give the optimal type for testing. Like for instance, the length function here, our logarithm operation will give the natural number type, to test this function. But actually, it's sufficient to use the unit type to test it. So our algorithm is still not optimal for some test cases, for some functions. Also, we can work on more expressive types like co-inductive types, non-regular inductive types, or even dependent types. Okay, so that's the end of my talk. Thank you.
Thank you. By the way, I made a mistake in the beginning. So the speaker is actually Zhuyang Wang. Sorry about that. So any questions from the audience? Okay.
Yeah, thank you for the very interesting talk. So my question is about ad hoc polymorphism or type classes. Have you thought about if you have a function that's polymorphic, but the type has some additional operations on it, if there's anything like this that can be done, or is it like completely intractable? Thank you.
Oh, that's actually a very good question. So for type classes, actually our theory, currently it cannot handle type classes, because, if we, like for example, if a function need a type class EQA for equality, if we don't have that type classes, but if we are passing a function from A to Boolean, if we are passing that comparator to this function, then our theory can handle it. But usually it's not the optimal way because of the first future work I pointed out. So we haven't done anything to the type class, but I think it's still doable.
We had another question here.
So in the case of the projection testing, for testing the projection function, another way to test this is to use a Boolean and many inputs that are one in exactly one place. And I'm wondering if how your approach compares to that kind of testing.
Do you mean the N-rate projection?
Right. So here you have a single test case with just the int type, but there's also another where you have a smaller type, like the Boolean type, but you have n input, one for each position. And do you have any insight on this kind of testing?
Oh, so if I understand the question correctly, if we are using a smaller type like Boolean, we do need more test cases to test this function, right? So, but in our case, we are trying to find the minimal number of test cases to test it. So, I think for the projection function here, it's actually better to test with fewer test cases. But there are other examples like, there are other examples like the filter function. There are two choices. We can either test it with Boolean or integer, but there are trade-offs between enumerating all the functions or enumerating all the lists. So yeah, that's still a problem we can explore.
Do you have any questions online? Yes, so the question, we have a question online. How can you automatically obtain the good form of the input even when the type is determined? Do you rely on the property specification you aim to examine?
Well, I don't think I fully get the word determinate. Is it? It's deterministic or something?
No, it's asking when the type is determined, I guess when it's known.
Well, actually, I'm not quite sure about the problem, but I think for we don't rely on other property specifications because we only need the type. We don't need to know the implementation or any specifications. So the only thing we need is the type. Yeah.
Oh, another online question. So the question is, it seems that only bool would be necessary for testing NRA-proj1, i.e. proj1 true, false, equals true. Is it accurate to say that the type A star is really a type sufficient to uniquely determine the overall behavior of a polymorphic function?
Yeah, so yeah, that's a good question. So I think for the binary projection function, yeah, actually the type Boolean characterize all the possible behaviors of that function. Because if we look at the type, it's actually very similar to the Church encoding of Boolean type in system F. So this function really has the same information as a Boolean. Yeah, that's right.
All right. Oh, one more question.
So if I understand correctly, your claim is that you need only to check the program in its special types and inputs, right? So, but the programs usually have a problem to handle some special cases and some special inputs, right? There are always some special inputs and types that program cannot handle it. But you didn't check it in for many types and inputs. How can you make sure that the program is correct?
Oh, good question. So yeah, I should say this before. So we are considering a pure language, and so all functions should be total, and there are no side effects or other things. So otherwise, the property of parametricity doesn't hold for polymorphic functions. Like for the identity function, in system F, there is only one way to implement it. But if we have side effects, then all the good properties are lost. So yeah, so our theory cannot handle like language that are not total or other things.
All right. Thank you. Thanks a lot. And let's thank the speaker, please.